Hello everyone, welcome to Lecture 7, which is entitled The 8 Planets. In this video, we're finally going to go through the 8 planets of our solar system in detail, one by one. Before we get to that, I want to talk about the solar system overall. I want to define what's in the solar system, and then explain to you how to clearly differentiate between the different kinds of objects. In so doing, I'm going to explain to you why Pluto is not a planet. I should also say that in this video, I'm going to reference other videos, smaller videos that I'm going to post to Blackboard. In a physical course, in physical space, I would actually show you those videos in order. In other words, we would stop at a particular slide, watch a video, and then continue. I'm not going to actually do that here for the sake of brevity, but what I want you to do is, at the appropriate moment when I mention this in the video, I want you to stop this video, watch the associated video on Blackboard. They'll be posted right next to this link, and then come back to this video. Let's start by defining what the solar system is. Well, the solar system is the planetary system in which we live. It has planets in it, but it's also a system that is based around a star. That star we call the Sun. And our solar system has 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Our solar system also has many dwarf planets. There are 6 recognized dwarf planets. I should also probably underline where I'm reading from. Here are the 8 planets, and here are the dwarf planets. There are likely many more, probably hundreds more, because dwarf planets are harder to discover than actual planets, than just things we call planets. I'm going to discuss with you the difference between a dwarf planet and a planet in a bit. But the solar system also has one star, the Sun. There's gas, and then there's thousands of what we call solar system bodies. Let's discuss the difference between a planet and a dwarf planet. Let's start with the idea of a planet. Before I get into the precise definition, I want you to just conjure up an image of a planet. Let's say Earth. When you think of a planet, you don't necessarily think of gas or rock. Maybe you do, but planets come in both forms. You can have gaseous planets, rocky planets. There can be rocky planets with very thick atmospheres, such as Venus, but you can also have rocky planets such as Mercury with basically no atmosphere. And then Earth has a thick atmosphere, but not as thick as Venus's. And then you can have gaseous planets that are huge. You can have gaseous planets that are somewhat smaller, such as Neptune, which is still a big planet, but not quite as large as Jupiter. What are some of the characteristics that all these planets share, however? One is that they're all spherical. That's one property. A planet is an object that has enough gravity so that it's spherical. Another property that a planet has is that its orbit is cleared of everything else around it. That's actually not a very precise way of saying it. What I mean is, let me try to restate that. That's not a precisely correct statement. A planet is an object whose orbit is cleared of other orbits in its immediate vicinity. That's a slightly better way of putting it. So in other words, if you look at the orbit of Earth, there's not an object orbiting right adjacent to Earth's orbit. There are planets, but they're reasonably far away. There are also asteroids that pass through Earth, but there's nothing that is, in a way, competing with Earth's orbit. Now, the second one is not something maybe you have thought of before, but if you've seen a picture of a solar system, then I think you'll agree that it's actually implied by the picture. If you see a picture of a solar system, it will look something like this, where the planets orbit in well-defined paths and the orbits are separated from each other. I just wanted to go through this activity with you to try to connect the precise definition to images that you've seen before, so that the definition doesn't seem quite so strange or ephemeral. Or ephemeral is not the right word, esoteric is what I mean. So in any case, let's go through the definition of a planet. A planet is a celestial body that is in orbit around the sun. That part I think you knew already. Has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium or nearly round shape. And C, this is the second part I mentioned, has cleared the neighborhood around its orbit. This is a maybe more straightforward way of saying what I was trying to say before. By cleared, what it means is that the orbit, I'll try to say this again, the orbit doesn't have orbits directly adjacent to it of other objects. Now let's define a dwarf planet. A dwarf planet is a celestial body that is in orbit around the sun. Is in orbit around the sun. Has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium or nearly round shape. And then C has not cleared the neighborhood around its orbit. And then D is also not a satellite. A satellite, by the way, is an object that's orbiting a planet. An object that's orbiting the sun, by definition, is not a satellite. An example of a satellite would be the moon. The moon is a satellite of Earth. I'm talking about the moon as in Earth's moon. There are other moons in the solar system. But there's also artificial satellites that we put into orbit around Earth, for example. Let's go further and define small solar system bodies. These are defined as all other objects orbiting the sun. These consist of tiny bits of rock and ice. Some of them are tinier than others. The word tiny here is a little bit ambiguous. So they can be, small solar system bodies can be asteroids that are large enough to, let's say, make the dinosaurs go extinct, or at least most dinosaurs go extinct. That's a relatively large rock. They can also be objects that are the size of a pencil eraser or smaller. This is an overview of the solar system stated in a relatively precise way. Let's talk about Pluto. Why is Pluto not a planet? Well, I actually don't have a picture here of, or an animation rather, of the solar system. I'm just checking all of my slides. So I'm going to attempt to draw this for you. I have a nice animation of the solar system that I will show you when we discuss the formation of solar systems. And this animation actually does a really nice job of depicting this. But the basic reason is that the orbit of Pluto clearly has not, clearly doesn't look like that of a planet. Pluto has not cleared its orbit of debris or other planets, or I shouldn't say other planets, of planets or debris. For example, these circles here represent roughly the orbits of the planets in our solar system, not to scale, obviously, not drawn very well. Pluto's orbit doesn't follow the same pattern here. It looks more like this. It's a highly elliptical orbit, meaning that it's not very circular. It looks much more like the orbit of an asteroid. Asteroids have orbits that are not really close to circular at all. They're highly elliptical. Also, the orbit of Pluto is directly adjacent to orbits of small solar system bodies in the Kuiper Belt. And so really, if we didn't know any better, if we looked at the orbit of Pluto, we would really view it as part of the Kuiper Belt, which is a region of asteroids and comets outside the orbit of Uranus and Neptune. That's it for my explanation of why Pluto is not a planet. As I said, I have a nice animation in another lecture video that I will get to later on when we do the formation of solar systems. And I think that animation will do this topic a bit more justice. For now, let's move on to Mercury, and then we'll work our way out. Mercury is the planet that is closest to the Sun. And as you might guess, Mercury is very hot. Mercury actually does not have the highest average surface temperature of any planet, but it does have the greatest difference between night and day temperatures. There's night and day on Mercury, and nighttime temperatures are exceptionally cold, something around minus 300 Fahrenheit. Daytime temperatures are often exceptionally hot. In fact, they're always exceptionally hot, and they can reach 800 degrees Fahrenheit. This is a massive swing. You might think that nowadays there are relatively large temperature swings. During the day it's reasonably, well, it depends on when you're watching this, but during the day in fall it can be reasonably warm, and then at night it can get quite cold. But notice that on Mercury the swings are fantastically greater. And one of the reasons, the primary reason, is that Mercury does not have an atmosphere. Our atmosphere on Earth holds in heat. And this is I'm referencing here the greenhouse effect. This is known as the greenhouse effect, whereby Earth emits radiation back out into space in the form of infrared radiation because of the surface temperature of Earth. It's in the infrared part of the spectrum. And some of this radiation gets absorbed by certain molecules in the atmosphere of Earth. This heats up the atmosphere, and therefore the atmosphere acts sort of like a planetary blanket in a way. It warms up the Earth. This also has the effect of distributing heat around the planet. Now, obviously, heat is not distributed evenly around the planet. There are certain places that are much hotter than others, obviously. But without any kind of atmosphere, the temperature differences would be greater, and they would also be greater between night and day. At night, there's no radiation from the sun hitting that part of the Earth. Let's say we're in New York, right? So at night, the sun is on the other side of the Earth compared to New York. It's on the Pacific side, the side of China and Japan and Australia, etc. So there's no radiation hitting the Earth on this side of the Earth during that time. Therefore, the Earth is just radiating back out into space. And if we didn't have an atmosphere, this would dramatically decrease the temperature. On Mercury, there is no such atmosphere. Mercury has... Okay, let me actually just go directly to the part of the slide that talks about the atmosphere. Just jump around a bit here. The atmospheric pressure on Mercury is about 1/trillionth that of Earth. I was going to try to describe the atmosphere, but I realize I have a definitive statement here. Therefore, this process I was just talking about, whereby the atmosphere heats Earth and distributes heat a little bit, does not exist on Mercury. There have been some missions that we've sent to Mercury. One of the themes in this course is the missions that we've sent to planets. It's to describe how we know what we know about the solar system, which is largely because we send craft to different planets and also near the sun. The most recent one is Messenger, which ceased operations in 2015. But we also sent a craft, we humans, called Mariner 10 in the 70s to Mercury. One of the characteristics of Mercury's surface that you'll notice when you take a look at it, which I'll allow you to do in just a moment, is that it's highly cratered. Mercury has huge cliffs, some of them 2 kilometers high. And when you look at the surface of Mercury, you might think that this looks very similar to the surface of the moon, which I'm sure you've seen before. And indeed, in a way, you'd be correct. And one of the things you should keep in mind is that when you see the surface of an object, whether it be a dwarf planet, satellite, planet, what have you, that is highly cratered, you should think that that object does not have much of an atmosphere. Another thing that our atmosphere does is smooth out the surface of the Earth. Now, clearly, we have craters on Earth, we have cliffs and mountains, etc. But compared to Mercury and the Moon, for example, which are objects that have basically no atmosphere, there are very few craters on Earth. And that's because the craters that have formed on Earth over billions of years have been mostly smoothed out. And they're smoothed out by weather, basically. Let's go through a couple other characteristics of Mercury. Mercury is largely metallic. It's a highly metallic planet. We're going to discuss how we interpret this in terms of the formation of the solar system later when we get to that lecture. Mercury's surface also contains things like silicon, potassium, iron, titanium, oxygen, blah, 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 uranium, and many other things. If you're interested, by the way, I have the links down here, so feel free to follow these links and then read more about the surface composition of Mercury or messenger or what have you. Let's now depict Mercury visually. Let's look at some pictures. This is from Mariner 10 in the 70s. I mentioned that when you see a picture of Mercury, you'll probably think it looks like the surface of the moon. And this picture in particular, I think, is reminiscent of that. This is a video that I'm going to show you from Messenger, which is the more recent mission that we sent to Mercury. I told you that I wouldn't show you videos within this video. This is an exception because this is relatively short. I do want to point out that this video has been color-coded to represent different materials on the surface of Mercury. And therefore the surface of Mercury does not have these wonderful blue, reddish colors as depicted here. But otherwise, this is a real video of the surface of Mercury. Now that that video is done, let's move on to Venus. Venus is the second closest planet to the Sun. It's also a rocky planet. I didn't say that explicitly about Mercury in this video, but I think you can tell from the pictures that Mercury is a rocky planet. And I mentioned to you it has basically no atmosphere. And the same goes for Venus, except Venus has a very thick atmosphere. Venus is the next closest planet to the Sun, and we've sent quite a bit more craft to Venus than we have to Mercury. These include the Mariner missions, Mariner 2, Mariner 5, the Soviet Venera missions, Pioneer, Magellan, etc. I did mention the size of Mercury, actually. Mercury is the smallest planet, and Venus is actually the third smallest planet. The second smallest is Mars. The fourth smallest is Earth. Venus is in between Mars and Earth. And Venus is actually nearly the same size as Earth. In terms of the radius, it's very close to Earth. It's about 95% of Earth's radius, but its mass is about 82% that of Earth. Venus is typically described as extremely uninhabitable. And by uninhabitable, I'm talking about with respect to life as we know it. In other words, if you were to take any creature basically and send it to Venus, you would not expect that creature to live any period of time. If we like, we can even look at this in a narrower sense and talk about humans. If we were to send humans to Venus compared to, let's say, the Moon or Mars or Mercury, we would find that Venus is particularly uninhabitable. That's what I mean by uninhabitable. And there are a couple of reasons why Venus is extremely uninhabitable. Venus is the hottest planet by average surface temperature in the solar system. Its mean surface temperature is roughly 860 to 870 degrees Fahrenheit. And you might think this is strange because it's not the closest planet to the Sun. But this is caused by a very powerful greenhouse effect which arises from its thick carbon dioxide atmosphere. The surface pressure on Venus is about 92 times that of Earth. If you're standing on Earth, there is a pressure, there are forces pushing down on you. In fact, it's not just down, it's on every part of your body. So it's actually up as well. If you hold out your palm in front of you, doesn't matter whether palm's up or down, but hold out your hand so that your 5 fingers are together, then the atmosphere is actually pushing down on the top of your hand and pushing up on your palm, or if you flip your hand the other way, pushing down on your palm, pushing up on the back of your hand with equal amounts of force. And that force is actually rather substantial. I won't try to describe to you what it is, but it's actually a surprisingly large force. And the reason why you don't feel that force is because these forces are balanced within your body, essentially. And not only are they balanced within your body, but actually these forces are exerted on the entire surface of your body equally. Okay, I don't want to get into a full discussion of this, but the point is that the surface pressure of Earth is actually quite substantial compared to certainly the Moon or Mercury. But the surface pressure on Venus is almost 100 times that of Earth. And this actually corresponds to about 1,300 pounds per square inch. You could translate this to a distance underneath the surface of the ocean. You could ask, how far down underneath the surface of the ocean would you have to go so that the pressure on you would be the same as that on Venus, just standing on the surface of Venus? And the answer is about 3,000 feet underneath the surface of the ocean. That's an exceptionally thick atmosphere, and the atmosphere is almost entirely carbon dioxide. Carbon dioxide is a greenhouse gas, which means that it absorbs infrared radiation. I'll show you pictures in just a little bit. Let's continue with the discussion of the atmosphere of Venus. And therefore, when Venus emits infrared radiation back out into space, a very large proportion of it is captured by the atmosphere. I'm just explaining once again the greenhouse effect. And this is such a powerful effect that it actually makes Venus the hottest planet in the solar system, even though it's significantly farther from the sun than is Mercury. The atmosphere of Venus is mostly carbon dioxide with some nitrogen and then some trace elements. Surprisingly, Venus actually has almost no magnetic fields. I say surprisingly because I've mentioned to you before that astronomers think that one of the reasons why Earth has kept its atmosphere over the course of its history is because it has a magnetic field. I talked about this in particular in reference to Mars. Venus, like Mars, has basically no magnetic field, and yet it has a very thick atmosphere. We would expect that the atmosphere of Venus is being continually stripped away by the solar wind, but there's evidence that there's volcanic activity which is likely replenishing the atmosphere. Let's talk about some other properties of the atmosphere. It contains almost no water, but it contains quite a bit of sulfuric acid, and it actually rains sulfuric acid on Venus. Now I want to talk about some other surprising aspects of Venus, in particular the atmosphere. The surface of Venus is very hot, and the surface pressure is very great. However, if you were to go up in the atmosphere quite a far distance, you would notice that the temperature eventually becomes more reasonable for human life, and the atmospheric pressure at great heights becomes more Earth-like. And so NASA has actually proposed sending humans to explore the upper atmosphere, since the upper atmosphere is more habitable in the strict sense I talked about earlier than the surface. I'm going to put a video of this proposed craft on Blackboard. I'm not going to actually play this video for you, except maybe the first few seconds, just so you know which video is which. This video here depicts the craft that I mentioned. This is a hypothetical craft that might be sent to the upper atmosphere of Venus, called the High Altitude Venus Operational Concept. Okay, I'm not going to play the video for you for the sake of brevity, but it's on Blackboard. So please stop this video temporarily and watch A New Way to Explore Venus, and then come back to this point. Let's look at some pictures of Venus from Venera. Well, there's not much to say about these pictures. I already talked about some of the surface properties of Venus, that Venus is extremely hot and the surface pressures are very great. As a result, it's very difficult to send craft to Venus, and spacecraft therefore don't last very long. This is unlike Mars, where we've sent craft that have lasted for years. In fact, we've sent rovers that have actually explored not a huge portion of the surface, because Mars in principle is a large planet if you're only traveling a few miles an hour, but we've nonetheless been able to explore a surprisingly large amount of the surface, given the fact that Mars is very far away. I want to mention one more thing about Venus, which you may have heard from the news, and that is that we may have found evidence of bacterial life in the upper atmosphere of Venus. In particular, there was a paper published. I don't have any information of this in the slides here, but I'm just going to go back to the first slide here where I talk about how Venus is uninhabitable. There was a paper published very recently claiming that the molecule phosphine has been found in the atmosphere of Venus. And this might be interpreted as evidence for life on Venus, bacterial life, because phosphine should break down very readily in the Venusian atmosphere. However, I should say that this is just one study, and this is a matter of chemistry, but it's not necessarily known absolutely that there cannot be any chemical or abiotic process that produces phosphine in the atmosphere of Venus. But phosphine has been regarded for quite a while as a potential biomarker, people call it, of life, because phosphine, generally speaking, is difficult to produce without life. It is produced in gaseous planets such as Jupiter, but Jupiter has much greater pressures and temperatures if you go into the planet than we have on Venus. But I do want to stress that this is not proof of life on Earth. We have to wait for verification of this detection of phosphine. There's actually a satellite which is going to be making a flyby. I shouldn't call this a satellite, it's a mission. I'm sorry that I'm forgetting the name. That's going to make a flyby of Venus actually within a few days, and this mission might be able to detect phosphine. So this is a very tantalizing result. It's possible we found life in the upper atmosphere of Venus, but this also could be a misinterpretation. So we have to be careful about this, but nonetheless, I wanted to mention this to you because it's likely you've seen this in the press. I should say that I don't necessarily think that journalists and the media have done a good job explaining some of the intricacies here. In science, we always wait for validation of results. We have to have different teams, so to speak, or different people make measurements, and then we have to discuss the results and make sure we're interpreting them correctly. The Venusian atmosphere is complicated, so it's possible people are missing a completely non-biological way of making phosphine. All right, that's all I want to say about Venus. The next planet is Earth, but we've talked about Earth already. In another video, we talked about Earth and the Moon. So I'm going to move on to the planet after Earth, which is Jupiter. Jupiter is the largest planet in the solar system. It is, okay, also, I'm sorry. You may be very confused right now. Sorry about that. I'm also forgetting that I have an entire video on Mars. Sorry. So the order of the planets goes from Mercury to Venus to Earth to Mars to Jupiter. I'm being a major doofus and I'm completely forgetting about Mars. So after Venus, we have Earth. We covered Earth already in a video. After that, we have Mars, and that planet is going to be the subject of an entire lecture, lecture 8. So I'm going to skip it for now, and then we go on to Jupiter. Sorry if I confused you there. Jupiter is the 5th planet from the Sun. It is a gaseous planet, and it's also the largest planet. Its mass is about 300 times that of Earth, and its radius is about 11 times that of Earth. This description of Jupiter is maybe not so intuitive because it might be hard to visualize what is 11 times larger. If you would like a visualization, please go to the first video that I posted. I think it's called Lecture 0. And in that video, I have a 2-scale diagram of all the planets. And then you can see the relative size of Jupiter compared to that of the Earth. In any case, the surface gravity is about 2.5 times that of Earth's surface gravity. And it might actually seem strange to talk about the surface of Jupiter because I just mentioned that it's a gaseous planet. Well, there's 2 things to say here. The first is that it very likely has a core, which is rocky and icy. But the second thing to say is that by surface, I'm not talking about the same kind of surface we have on Earth. So I'm not saying that you go into the a gaseous planet such as Jupiter and then suddenly you hit rock. That's not what we mean. What we mean by surface is some arbitrary point within the gas that forms Jupiter that has roughly the same, I shouldn't say the same, but has some standard pressure. So we define a quote-unquote surface that has some kind of pressure within the atmosphere of Jupiter, and then we just refer to that as the surface. And so it's not a real surface in the sense of a terrestrial planet. This is the way in which we're defining the so-called surface gravity. It's the gravity within the atmosphere to some arbitrary but well-defined point. Jupiter has quite a few moons. Actually, new moons are being discovered not all the time, but reasonably frequently. But the most recent count as of when I made these slides is 67 moons. There are 4 massive ones. There's all of them have mass, but the 4 most massive ones in particular are Ganymede, Callisto, Io, and Europa. I'm going to talk about Europa a little bit in this video because it's one of the places where we think we might find life in our solar system, assuming we haven't discovered it in addition on Venus as well. Jupiter has a very strong magnetic field. It's roughly 10 times as strong as that of Earth. I mentioned that it likely has a small rocky core. Just a tidbit of fact about the atmosphere. If you travel into the planet, the atmosphere increases, as you might expect. At an atmospheric pressure equal to that of Earth's surface, the temperature is about minus 108 Celsius. And so you can say that roughly this is the surface temperature of Jupiter. Again, we're using surface in a non-literal sense. One thing that I want to point out here is that as we go out from the sun, the planets get increasingly colder, with the exception of Venus, which is the hottest planet on average. But Earth is cooler than Venus, thankfully. Mars is cooler than Earth. And then Jupiter is even cooler than Mars. And then the same rule applies as we go out from Jupiter to the other gaseous planets. Jupiter has a great red spot. This is maybe the best known surface feature of Jupiter. This is a giant storm, which is about twice as wide as that of Earth. The winds in the Great Red Spot reach somewhere around 400 miles per hour. I'll just show you the spot here. Let's talk about the interior of Jupiter. Actually, for the sake of brevity, I'm going to pretty much skip everything and just once again mention that Jupiter likely has an icy rocky core, and I'll skip everything else. You can treat this slide as extraneous information. There's a lot of information here, so let's just move on to the magnetic field of Jupiter. I mentioned that it's very strong, and you would expect, therefore, Jupiter to have aurorae. We talked about, as you recall, the northern lights on Earth, for example. These are lights you see in the northern hemisphere near the poles that arise from charged particles being captured by Earth's magnetic fields and then being dragged into the poles. And they're dragged into the poles because Earth's magnetic fields forms loops. These loops pass through the poles in roughly straight lines and then loop around from one pole to the other. Jupiter also has these lights for the same reason. This is a picture of an aurora on Jupiter. This has been enhanced. It looks a little bit cartoonish. It is a real picture, but the visualization has been enhanced so you can see it more clearly. But there are indeed lights that are formed on Jupiter for the same reasons they're formed on Earth. As I mentioned earlier, one of the themes in this course is to explore the missions that we've sent, and we want to apply that to Jupiter as well. We've sent a number of missions, including the Pioneer and Voyager missions, Ulysses, Galileo, Cassini, and Juno. Juno is the most recent mission, and it was launched in 2011, and it's taking, I think I have a whole, no I don't, I'm sorry. Okay, so I'll just talk a little bit about Juno. I thought I had a whole slide on it, but I don't. Juno is looking at mapping the gravitational field of Jupiter, as well as exploring the magnetic field in more depth. All right, that's all I want to say about Juno. Let's talk about some of the moons or satellites of Jupiter. The largest is Ganymede, which is actually larger than Mercury. And then we have Callisto, Europa, and then Io. Let's direct our attention toward Europa. There's an awful lot to say about the moons of Jupiter. We could spend a whole lecture just on the moons of Jupiter, but obviously we don't have time to do that. Let's instead just focus on Europa, which has actually garnered quite a bit of attention because many people think that there's a good chance that there's life underneath the surface of Europa. And the reason is that the surface of Europa is water ice. It's a thick water ice surface because Europa is quite cold. Remember, based on how we define the surface of Venus, the surface temperature is roughly minus 100 degrees Celsius on Jupiter, which is quite cold. And you would expect the moons of Jupiter also to be very cold. But underneath the icy surface of Europa, we have an ocean of liquid water. And we have actually direct evidence for this liquid water, so we're quite sure that it's there. And there's an awful lot of water, much more water on Europa, or in Europa, if you like, than we have on Earth. And the reason why there's an ocean of liquid water is because Europa is being heated by tidal forces caused by its orbit around Jupiter. Jupiter is a much larger planet than Earth, as we talked about earlier. And as Europa orbits Jupiter, Europa actually gets squeezed and elongated. It's a little bit like one of those squeeze balls that you might squeeze to get rid of stress. Maybe a toy for a dog or something like that that squeaks, something like that. As you squeeze it and let it go, over time it gets hot. And the same thing applies to Europa. I'm exaggerating a little bit with the magnitude of the squeezing. It's not that Europa is getting crushed and then elongated, but nonetheless, the squeezing and elongating of Europa is enough to actually heat the inside of the planet to the point where there's liquid water. This is described in a video called Europa Ocean World. I'll just play for you the first few seconds. I would like you to watch this video on Blackboard.
Search for life beyond Earth.
Okay, that's all I'm going to play for you just so you know which video is which. I would like you to watch that video because there's, for one, nice animations of the tidal forces on Europa, as well as other good information. The surface ice of Europa may be only 2 or 3 kilometers thick. We don't know actually how thick it is. It might be too thick for anyone to feasibly drill, but if it's only around 2 or 3 kilometers thick, which is on the thinner end of what the data is indicating, then it's possible sometime in the future we could actually dig through it, and then we could see what's in the liquid ocean surface. I should say that we have directly observed cracks forming and liquid water reaching the surface and then freezing. So this is part of the reason why we're quite sure that there is indeed liquid water down there. Now, there is really no light that's going to reach this ocean. However, that's not necessarily indicative of this ocean being inhospitable to life or uninhabitable. And that's because on Earth, we have many environments underneath the surface of the ocean that are basically completely dark, and yet they're very habitable. They're teeming with life. And these are referred to as hydrothermal vents. These are places at the bottom of the ocean where the heat from inside the Earth is coming up, sort of like volcanoes or just hotspots on the surface of the Earth where the heat is coming up. This is geothermal activity, generally speaking. And you can have this at the surface of, at the bottom of the ocean. And these are called hydrothermal vents. The temperatures can reach almost 800 degrees Fahrenheit near these vents. And these vents often emit some chemicals that are very noxious or toxic to humans. One is hydrogen sulfide. Perhaps amazingly, or not so amazingly, life has actually formed in these hydrothermal vents, and in fact there's tons of life. This was discovered in the 70s and changed our perception of life in a way, because before then it was thought that life could only exist directly or indirectly from the sun, or based on sunlight, I should say. For example, even we directly require sunlight, in the sense that when sunlight hits the skin of our bodies, it actually helps us produce vitamin D. People who live in regions of the Earth where there's very little sunlight sometimes have vitamin D deficiency. But of course, we indirectly rely on sunlight because we eat plants or other animals. Plants obviously depend on sunlight for photosynthesis. Other animals that we eat would either eat other animals or they would eat plants, which of course depend on the sun. But these hydrothermal vents are examples of regions on Earth where there's life, but this life does not depend really at all on sunlight. And this can serve as a template for thinking about life on Europa. Perhaps there are hydrothermal vents at the bottom of this ocean on Europa, and perhaps there are life forms, maybe even somewhat similar to what we have on Earth. On Earth, we have bacteria, worms, fish near these hydrothermal vents. I'd like you to stop this video and watch this one, The Discovery of Hydrothermal Vents, which is actually narrated by Bill Nye. You may be familiar with Bill Nye. This is the video here. This is a really nice video where he talks about Europa in the context of the discovery of hydrothermal vents on Earth. When you're done with that video, please come back to this one. In particular, come back to, I should say actually, if you like, this is more optional. You should really watch all the videos I just mentioned. I would suggest watching this one as well after the Bill Nye video. Unfortunately, there's a technical issue not allowing me to play this video. That's okay. But there's a video called Pescadero Basin, which doesn't talk about Europa at all. It's just a rather nice video on, nice is not a very good adjective, a rather eye-opening video on the hydrothermal vents in the Gulf of California. But this one's not as pertinent to the course. When you're done watching either both or at least the first of those videos, please come back to slide 19, where we finish up talking about Jupiter. I said earlier I don't have a slide on Juno, but I was actually incorrect. I had forgotten that I put the slide at the end of the Jupiter section. Let's talk about some of the things that Jupiter is trying to measure Jupiter. Some of the things that Juno is trying to measure vis-a-vis Jupiter. It is attempting to measure the amount of water in Jupiter's atmosphere. It is attempting to peer deeper into the atmosphere to determine temperature, composition, and cloud motion. And then this third one I mentioned, it is trying to construct maps of Jupiter's gravitational and magnetic fields. Let's move on now to Saturn. Saturn is the second largest planet. Its mass is about 95 times that of Earth, and it's cooler than Jupiter. This rule now that as we go outward from the sun, the planets get cooler and cooler is absolutely true. The only exception would be Venus. I did mention to you the composition of Jupiter, actually. The gases are mostly hydrogen and helium. The same thing goes for Saturn and the rest of the gaseous planets. Actually, I just want to spend a minute talking about why that's true, or I won't really tell you why. I'll just tell you that it is in fact true that if you look at any reasonably large gaseous object, such as even a planet or certainly a nebula, which is a giant cloud of gas and dust, you will see that this gaseous object is made of hydrogen and helium primarily, with some trace elements or molecules. And the reason comes from the early universe. Maybe I will tell you the reason just very briefly. It's because in the early universe, hydrogen and helium were the only two elements that could have been produced in large quantities. This we will talk about when we get to cosmology. I'm going to leave the rest of the discussion for the end of the semester when we get to that lecture. Saturn has 62 moons. The largest moon is Titan, and then there's some other moons as well. That's not horrendously important. One of the major features of Saturn that you will notice if you take a look at it is that it has rings. Saturn's rings are the most prominent rings that we have in the solar system, and there are actually people who just study the rings, believe it or not. I actually watched a video of this talk by this planetary scientist, I forget her name, who has spent her whole career just studying the rings of Saturn. I watched it in order to prepare to lecture about Saturn, and I wanted to incorporate some of this wonderful information, but it would just take up too much time. But I do want you to know that these rings are very complicated, and scientists actually categorize different parts of the ring, or rings, I should say. That's all I will say about that. If you are interested, you can Google videos of Saturn's rings, and you can find out all kinds of interesting information. The rings are composed of ice, primarily, reasonably small chunks of ice. Here's a wonderful picture that I showed you near the beginning of the semester. I actually showed you, I don't think it's precisely this picture, but it's something similar. And as you recall, there was Earth in the picture. This is, I shouldn't say analogous. This is a very similar kind of picture, photo, but slightly different. But nonetheless, you can see, well, perhaps you can see Earth and the Moon in the photo, as well as Venus and Mars. I actually cannot see Earth and the Moon in this photo, but if you zoom in, if your eyesight is good, perhaps you can see a dot. I actually do have a little information about Saturn's rings. I'm sorry, I keep forgetting exactly what I have in my slides. You don't have to memorize these. I just want you to know that the rings are complicated. That's it. You don't have to know anything else about them. As I said, if you're interested, you can Google information, and in principle, we could have a whole lecture just on this. Saturn's largest moon, Titan, has a very thick atmosphere. You should know some basic facts about Titan. Its atmosphere is about 60% greater than Earth's, measured by surface pressure. The temperature is very low, roughly minus 300 degrees Fahrenheit, almost 200 degrees Celsius, minus 200. The Cassini spacecraft examined the surface of Titan via radar. And this is an image of the surface. Let's go on to Uranus. Uranus is the seventh planet from the Sun. It's the one that is almost the farthest out from the Sun. The farthest out being Neptune, which we'll get in a little bit. It is Also very cold and very large, but it's not quite as massive as Saturn or Jupiter. It's actually only 15 times that of Earth in terms of mass. It is once again composed mostly of hydrogen and helium, and its surface temperature is smaller than that or lower than that of Saturn. This is a pattern that I mentioned to you. Uranus emits UV light, creating what's called a day glow, and you can see this a bit in the picture here of Uranus. Let's finally move on to the last planet, the farthest one from the Sun, which is Neptune. Its mass is about 17 times that of Earth, so it's roughly the same mass as that of Uranus. It is once again colder than Uranus, and Neptune actually has a great dark spot, which is similar to Jupiter's great red spot. I've gone through the last couple planets very quickly, in part because the terrestrial planets are more interesting from the perspective of understanding Earth. That's one reason why. So sorry for the bias there toward terrestrial planets. But nonetheless, that is my introduction to the 8 planets, leaving out Earth, which we covered, and then also Mars, which I embarrassingly forgot about earlier, and we're going to do Mars in Lecture 8. Thank you for watching this video. I hope it was enlightening, and I will talk to you in another video.